We all know AI is incredible, right? It can drive cars, discover new medicines, even create stunning art. But this genius has a secret. It's shockingly fragile. So today, let's dive into why telling an AI exactly what to do, writing simple, logical rules for it, is one of the biggest challenges in all of computer science.
Okay, take a look at this. An AI looks at this image and correctly says, that's a panda. Simple enough. But then we add a layer of what is essentially invisible static, just tiny changes to the pixels, and suddenly the AI is 99.3% confident it's looking at a gibbon. And this isn't some random glitch, it's what we call an adversarial example, and it exposes a massive vulnerability in how these systems see the world.
So the obvious question is, right, can't we just write a rule to stop this? Something simple that just tells the AI, hey, don't do that. Well, it seems easy, but this is exactly where our problems begin.
So let's try it. Let's actually try to build that rule ourselves. Our goal is to create what's called a formal specification, basically a precise, logical instruction to prevent these kinds of mistakes.
A formal specification sounds technical, but you can just think of it as an ironclad contract for the AI. It's a mathematical guarantee that leaves absolutely no wiggle room for misinterpretation. So what would that contract look like for our panda problem?
Here's our first shot at it. And you know what? It sounds perfectly reasonable. If two images are almost identical, the AI shouldn't be confident that they're two completely different things. This should stop the whole panda to gibbon thing cold. It's simple, it's logical, and it turns out it's a complete disaster.
With that one simple rule, we've basically created a logical time bomb. And what's so fascinating here is how this one seemingly perfect idea leads to a conclusion that is just completely absurd.
So before I spill the beans, just take a second. Look at that rule again. Can you see the crack in the logic? That tiny loophole that could bring the whole thing crashing down. How could an AI follow this rule perfectly and still get everything wrong?
Are there unintended consequences? Oh, you have no idea. This rule doesn't just have a small side effect. It completely and utterly breaks the entire system.
Here's the problem. The rule creates a logical chain. It's basically like a game of telephone for images. Imagine image A is our panda. It's nearly identical to image B, which has just a tiny bit of noise. Our rule says they have to be in the same class. Okay, fine. But image B is also nearly identical to image C.
So the rule says B and C also have to be classified the same. Well, if A is like B and B is like C, then our rule implies that A has to be treated the same as C. If you keep repeating this process with thousands of tiny, imperceptible changes, you can build a chain that slowly morphs that panda into an airplane. The start and end look nothing alike, but they're connected by this unbreakable chain.
And here it is, the catastrophic failure. If you can logically link a panda to an airplane, our rule forces the AI to classify them as the same thing. To satisfy this one simple rule, the AI has to conclude that all images, pandas, gibbons, airplanes, everything, belong to the same category. It becomes completely useless.
Okay, so yeah, that rule failed spectacularly. But this is how research works, right? You iterate, you try to fix it. So let's walk through 3 attempts to patch this broken rule.
Attempt number 1. The real problem was that word confidently, right? It created that ironclad, unbreakable chain. So for our first fix, let's just add a little bit of wiggle room.
See what we did there? We just took out that strict confidence requirement. It loosens the contract. Now the links in the chain are weaker. The AI doesn't have to classify them identically anymore. The chain that caused the total collapse, we've broken it.
So, did it work? Well, yes and no. The good news is the AI no longer thinks every single thing in the universe is a panda. So, phew. But the bad news is we are right back where we started. Now the AI is free to once again flip its classification from panda to gibbon with just a few imperceptible changes.
All right, let's try attempt number 2, a totally different angle. Maybe the problem wasn't the logic itself, but our definition of similar. So far, it's just been about pixels. What if we try to inject some actual meaning into the rule? Let's add a new condition: similar semantic features.
Now the rule is much tougher. It's not enough for the pixels to be alike. The images also have to be similar conceptually. For example, The rule might only kick in if the AI has already determined that both images contain a cat. This would definitely stop a chain that tries to morph a cat into a car.
This is an improvement for sure, but it just kicks the can down the road, creating a brand new problem: who defines semantic features? I mean, what's the mathematical definition of catness? You can't write one. It means a human has to sit down and try to define these concepts, which is totally subjective and pretty much impossible to do for everything in the world.
So that leads us to attempt number 3, and this one is a bit of a mind bender. What if we've been focused on the wrong thing this whole time? Instead of demanding the final one-word label be the same, what if we require the AI's internal reasoning to be similar for similar images?
This is a much more sophisticated approach. We're not just looking at the final answer anymore. We're looking at the AI's internal list of scores for all possible classes. The new goal is to keep that whole list of probabilities stable when an image changes just a little. It's a better solution, but it really shows you just how deep this rabbit hole goes.
This whole exercise, from our one simple rule to these much more complicated fixes, it really reveals the fundamental trouble with writing specifications for AI. And it turns out the difficulty really depends on the task. I mean, just look at these two examples. On the left, a non-perceptual task, an aircraft avoidance system. Its inputs are just numbers: speed, altitude, distance. It's actually pretty easy to write a hard rule for that, like if distance is less than X, then climb. But on the right, you've got a perceptual task, a self-driving car. How in the world do you write a perfect mathematical rule for that pedestrian might step into the road? You can't.
And that, right there, is the core paradox of all of this. For these really complex, messy, perceptual tasks, if you could write a perfect set of rules that covered every single possibility, you wouldn't need the AI to begin with. The whole reason we use AI for these things is precisely because we can't write down all the rules ourselves. Which leaves us with this final, massive question. We're trying so hard to write these perfect, logical rules for an AI to mimic human reasoning, but is our own reasoning something that can be boiled down to formal rules? Think about it. Our laws, our social norms, our common sense, they're all messy and filled with exceptions. Maybe this whole struggle to write rules for AI isn't really about AI at all. Maybe it's just holding up a mirror to how complex and how hard to define intelligence itself really is.